Battery down or something? Can you check?
Yeah, I'll have some. Are you plugged in?
So I don't have any batteries here.
No, I got some. Check 1, 2, check, check. Should be all set.
Thank you. How do you kids make it so early? How's the course been for you so far?
It's tough.
Are you going back to Doha at the end of the semester? Talk to me afterward class, okay? I would love to. Hey, Jeffrey.
Johnson family business in October or something. All of it goes well.
Thank you.
And you check the poll, please.
The poll? The poll hasn't posted. That seems off. Okay. So if any of my TAs is online, can you please check the polls? The poll itself was posted last night. We just had to open it up. Getting the timing right is always a challenge. We're pretty much prepared for the class the night before the class, everything is up, but then we have to release it at the right time. That means my poor TAs have to wake up at the right time. That's a challenge.
Lots of people is a little troubling, sir. I'm just saying a lot of people is a little troubling.
That's
I
what
don't see that many people in class today.
I know. Just keep, well, I'm hoping that more people will trickle in slowly. But okay. So it's time. Let's start. 757, that is a plane, right? Okay. Shut your laptops, guys, unless you're signing up for the attendance poll. The class keeps getting emptier and emptier as the semester progresses. It's kind of challenging. Starting next week for 4 weeks, I'm going to be away in India again. So the classes will be on Zoom. Labs will continue to be in person. And boot camps and such like will also be in person. So please do attend. And as it happens, the labs are a lot more important than the lectures themselves, which you can watch on video later, right? So it's important for you guys to actually watch, pay attention to the labs, because that's where you learn how to do real things. Anyway, let's begin. So what were we speaking of, Myra, in the last class? And what else did we talk about? We went into detail on on something. What?
Yeah, I could not recall. Sorry.
Oh my good God. Anybody else, can you tell me? What did we do in the last class? We talked about different layers. Okay, guys, I kind of imagine that most of you would be lost by now. So I'm going to spend a few minutes actually going back through what we did. So here's the story. So far, we saw that pattern classification tasks, such as does this picture contain a cat, are best performed by scanning for the target pattern. Scanning with an input with a network and combining the outcomes is equivalent to scanning with the individual neurons hierarchically. We saw that too. And so for 2D, two-dimensional or higher dimensional scans, we call this a convolutional network. If you're just scanning only across time, then we call this a time delay neural network terminology. And so a convolutional neural network, a time delay neural network is just an instance of a convolutional neural network. So a CNN, we saw, comprises convolutional and optional pooling layers. And the final layer is generally followed by a classifier, which could be an MLP or just a simple softmax. So the convolution layers, again, each convolution layers, within each layer we had a set of maps, which we also call channels. So if this is a layer, within each layer we had a set of maps, which really, going back to our scanning MLP analogy, represents the outcomes of scanning the previous layer with a neuron. So each of the maps represents what we got when we scanned the previous layer with a single neuron. Yes?
Just as a refresher, each output channel is associated with a filter that is the same number of dimensions as the number of input channels.
That is correct. Okay, and so within each layer, when we had a convolutional layer, each channel was computed, obtained by simultaneously scanning all of the previous layer channels, and you got a bunch of these channels, or maps. I'm going to call them maps or channels alternately. And so each map was computed in this manner. For each map, there were two operations that happened. The first was a affine operation, which computed affine functions of all of the previous layer maps through a filter, which is the only learnable component of the convolutional network, and besides the final MLP. And then once the filter had scanned the previous layer, we applied an activation pointwise. So the Z was the So when you computed the affine map, we saw this. We have as many output maps as affine maps as the number of filters. And so the inputs are all of the maps of the previous layer. And so in order to compute any particular output, we chose the corresponding filter, placed it on top of the collection of maps of the previous layer, and scanned it to get the output. Everybody remember this? Yes, no? Okay. And so this gave us the affine map Z. And then we applied an activation function pointwise to get the final activation map, right? So here's a more explicit illustration. Each output map over here, each Z, is dependent on every one of the incoming maps, incoming channels. So every Z is dependent on all of the Ys, and the dependence is through a filter, where the filter itself has as many channels as there are input maps, right? So this way, and so also every input map outputs influences every Z. So the Z's, the affine maps, are computed from the collection of input maps, and then the activation is simply applied pointwise on the Z's to get the Y's. So this was the convolution layer. Here's your first ball. I'm going to need his help. I'm going to need his help to pronounce it. So is the poll not coming up?
I got the 10th poll.
So guys, can we, all right, let's hold off on this one. But yeah, I'm still going to call out the Pokemons. Can you just tell the people, everybody to release the polls? Who's Lairon, L-A-I-R-O-N?
Oh, Lairon.
Release the poll skip. Yeah. So who's Lairon? So Lairon's absent, okay? Do we have another name? Yes. Who's Caterpie? C-A-T-E-R-P-I. Caterpie. Who's Caterpie? Caterpie is absent. Oh my good God. Okay. And who's Shiftry? Who's Shiftry? So when that would be you. All right. Okay. Is the first statement true? Yeah. All right. Guys, at some point of this, mark all of you absent. Okay. Who's Cedra? S-C-A-D-R-A. The second one, true or false? False. All right. And who's Lotad? L-O-T-A-D. Yes, the third statement. False. Thank you. And who's Himontop? H-I-M-O-N-T-O-P.
Himontop.
Himontop. Okay. Himontop is absent. And who is Pichu? P-I-C-H-U. Yes, the last statement. True. True. Okay, guys, the reason I have these Pokemons is because I don't want to leave the people on Zoom behind. I don't want to call you out by name. And so if I don't actually have a mechanism for invoking the people on Zoom, then I'm just going to be speaking to the people on class. People on Zoom get left out. And so I do this, you have to humor me. If you're not there in class, if you're not going to be paying attention, then the whole point is moot, right? So please. All right. So only the first and the last statements are true. The number of channels in any filter equals the number of input maps, and the number of filters equals the number of output maps, okay? Everybody with me? So the other layer we saw was the pooling layer. And the way that we performed pooling was that we considered a window of the input, and within each window, if you were performing max pooling, you just pick the largest value and scan the input. So if you saw the pseudocode, at each location, you picked the location of the largest element and stored it once you identified the location of the largest element. And then you copied the value at this location over to the output. Now, this two-step process is going to be important. We'll see why in a bit. The other pooling operation was mean pooling. We just took the average of all the elements within the map and scanned the input using this operation, right? So once again, here's the pseudocode for mean pooling. At each point, you're just considering a little window of the input and just copying the mean of that window over to the output, right? And so The other operations we saw were resampling. You can proportionally decrease or increase the size of the maps by dropping or inserting zeros. If you're downsampling, you'd be dropping s minus 1 rows or columns between rows and columns. If you're upsampling, you're going to be inserting those. So this was a downsampling operation. If I downsample by a factor of 2, I'm basically erasing every second column and every second row and then compacting everything that remains. And if I'm upsampling, I'm just inserting zeros between rows and columns. And we also saw that if convolution or pooling is followed by a downsampling layer, it's easier to implement it as just convolving or pooling with a larger stride. And upsampling must be followed by convolution. Upsampling by itself does nothing because you're just going to have a bunch of zeros left over. And so upsampling is often called convolution with a fractional stride because it's like taking a smaller stride to increase the size of the map. Now, so although when you actually look at the architecture of the network, they're going to mention this as in terms of strides. So they will say it is pooling with a stride of 2 or convolution with a stride of 3. But when it comes to the viewing it conceptually, it's always much, much simpler to view it as a standard convolution or pooling with a stride of 1 followed by downsampling. And this is, I cannot emphasize this enough. If you don't do this, then when you begin trying to work out the backpropagation rules, you're going to get so tangled, it's going to be hard to untangle you. So also convolution with a fractional stride is always, always, always best thought of as upsampling followed by regular convolution with a single stride of 1. Everybody clear on that? Right, okay. And so here's how we performed computation in a CNN. If you had a picture, you'd compact all of the channels, the color channels, and then you'd have a series of convolutional and pooling layers. And the terms that we could learn were only the parameters of the filters and any parameters associated with the final MLP. So the question is, how do we learn this? That's what we're going to spend this and part of the next class on. Training, as in the case of a regular ML, is exactly as in the case of a regular MLP. The only difference is in the structure of the network. So you're provided training examples of the image and its class. We define a loss, basically and then which is basically a divergence between the desired and actual output of the network. The actual loss is going to be the average of these divergences over the entire training set or your batch. And the network parameters are trained to minimize the loss through variance of gradient descent, which means we need to compute gradients, and this must be computed using backpropagation. So I'm going to be talking about derivatives in this class, but I want you to keep in mind that I'm speaking of gradients. What was the difference between derivatives and gradients? The gradient was the transpose of the derivative, otherwise the math does not work out, right? So here's what you would do. You'd actually pass your input, each training instance, through the entire network. You get some output. You have a desired output. You compute a divergence. And so the problem setup is as before. You're given a training set of input-output pairs. You define a divergence on each individual training instance. You have an aggregate loss, which is the average divergence over your training set. And then you want to minimize this loss using gradient descent. So there again, as your loss. And the gradient, or the derivatives here, with respect to the individual components, are simply the averages of the derivatives of the losses for the divergence for the individual training instances, which means that this term here needs to be computed. And so we're going to see exactly how to compute that. Now for training, it's the same process as before. You have a forward pass. Everything is passed through the net till you get your final output. And then you store all the intermediate values. Now, backpropagation through the final MLP is exactly the same as before. Here comes my lovely trident. I can point things with it. Now here, if you look at the picture over here, there's an operation that happens between the final convolutional layer and the MLP. And what would that be? What allows us to connect from here to here? You flatten everything, right? And so what this means is that at this final layer, all of these guys are unraveled. and then you can you can compute your MLP on this. So when you go backwards, you're going to you're going to obtain a loss derivative with respect to each of these guys. Those can be folded up back into the shapes of these maps. And so now you have a loss derivative with respect to every element of every map in the final layer. Everybody clear on this, right? And so we got to figure out how to pass those derivatives backwards. And we have to take into consideration the fact that the computation has shared parameters, right? And then you also have pooling. So let's first look at the convolution. When I'm performing convolution, here's what happens. You have some divergence. As I'm back propagating, I would have the derivatives with respect to the final activation maps. And so the question is, how do I pass the derivatives back from the activation map to the affine maps here? And then from the affine maps through to the previous layer, and also to the filter. And so for the convolution, again, the assumption is I already have the derivatives for every one of the elements for every one of these maps. And so what we really need to know is, how do I pass these derivatives back to here to get derivatives out here? And how do I compute the derivatives for these filters? Everyone clear about the questions here? Okay. So for the pooling layer, it's a very similar situation. The pooling operates channel-wise. So you'll be performing pooling on each channel to get the corresponding pooled output. We assume that we have the derivatives for these guys. The question is, how do I go back and compute the derivatives for the ones below, for the input to the pooling, okay? So here's the complete set of operations. We need to compute the derivatives for figure out how to back propagate derivatives through convolutional layers and how to back propagate them through pooling layers. Let's look at convolutional layers first. First, given the derivatives for the activation maps, how do I take a step back and compute the derivatives for the affine maps, right? So again, I have the derivatives for this guy, y. How do I compute the derivatives for z? So I have d div, let's just call this guy right over dyij. I'm not going to be sure. And I have y equals f of z, right, at each location. How do I compute dd over dzij? Anybody, how do I do this? This is an easy question. So maybe you can give me a Pokemon if nobody will reply. Can you call that out?
Rhyhorn?
Rhyhorn, who's Rhyhorn? Okay, Rhyhorn's absent. Come on, guys, this is a very simple question. So can you, okay, all right, Ankit.
I'm here.
Okay, what's the answer, Rhyhorn?
I think you just do it like element by element. So it's just partial y by partial f.
So partial y, what is that?
Right.
Okay.
Times by the derivative of the activation function.
Okay, so it's going to be dd over dy times f prime of z. This is all it's going to be, correct? Everybody agree with me, right? And so that's it. The derivative with respect to z is the derivative with respect to y times the derivative of y with respect to f. This is simply dy over df. Sorry, dz, which is simply the derivative of the activation function. So this was easy, element-wise. Everybody clear with this, about this so far, right? Nothing fancy. So we have managed to get the derivatives out at z. The real challenge is this one. How do I go back from z to the layer before it and to the weights? So again, how do I compute my perform back propagation through my affine map? So during the forward affine computation, I have got the z's from the y's of the previous layer and the filter, corresponding filter. So back propagation, given the derivative with respect to the z, I want to compute the, with respect to this guy. If I can go back. Oh my God, I think I'll just keep going forward. All right. So given the derivative with respect to z, how do I compute the derivative with respect to y? And how do I compute the derivative with respect to filter parameters? So again, oh, this is a better picture. I have the derivatives here. This has been computed from these fellows using these filters. How do I propagate these derivatives back to this and get derivatives for this one as well as the filters? Okay. Questions? Anybody? No. So let's just first consider the derivatives for the y's. How do I get this one here? Okay. Now, if I consider any single z, so let's consider the nth z. This would have come from the nth filter, right? The nth filter is going to be applied to the input to compute the nth output channel. And the nth filter, in turn, the filters themselves have channels. And so the filters themselves have as many channels as the input channels. Remember this, right? Because each channel of the filter got placed on the corresponding input channel. So every one of these input channels, maps, influences every element over here in the z through the corresponding channel of the corresponding filter. So let's say the mth input map is going to be influencing the nth output channel through the mth channel of the nth filter, right? And again, expanding it, I'm just simplifying this picture. So now every z is influenced by every y. Every y in turn influences every z, right? Everybody clear about this? And the divergence itself is computed from all of these z's. Eventually, all the z's go through the rest of the network. You get an output, you compute a divergence from it. So if I want to compute the derivative of the divergence with respect to, say, the elements of this map, I have to just consider all the paths that lead from that y to the divergence, which are shown here. Does this make sense to everybody? Right. And furthermore, every element in y over here, so if I want to sum this up, if I want to compute this, what I really will have is a sum over all of these maps of the derivative of the divergence with respect to the elements of these maps times the derivative of this elements of this map with respect to the y's. Everyone with me? Right, okay. So this term, we're assuming that the derivatives for this guy are already known and that they're arranged in the same shape as the map. So what we really want is, what is the derivative of the z with respect to the y? Okay. Now, let's consider, again, the y influences all the z's. Let's just consider one of these z's. How do I compute the derivative of this z with respect to the elements of the, of the y? Okay. Now, to do this, let's go back to an animation that we saw earlier. Now, the z itself is a map. It has many elements. The input y is also a map. It has many elements. So to compute the derivatives of the elements of z with respect to the elements of y, we have to figure out how each element of z has been influenced by each element of y. And so to see that, let's go back through this little animation. Now just notice the one y element. Again, the green picture is the input channel, the input map. The orange is the filter. And the blank picture to the right is the output z channel, right? And so I'm trying to figure out how the one little element that has been highlighted in red influences the elements of z. Okay? So as the filter goes through the scans the input, how many of the output elements did that highlighted element actually influence? Which ones? Only those guys, right? And so 4 of 9. So it's not 2/3, it's 2/3 each way. Right. So if I want to compute the derivative of the divergence with respect to this element, I must sum over these four guys. Right, but then again, remember that across all the channels, I have all of these Z channels. So this element influences these four elements of Z for every output channel Z, right? And so when I compute the derivative of the divergence with respect to this guy here, I must sum over all of these output affine maps, and over all of the output affine maps, I must sum over all of the elements that were influenced by this particular element. That clear to everybody? Right, this is just straightforward application of the chain rule, nothing fancy. So then again, we have the elements of, we have the derivatives of the divergence with respect to the elements of Z. So what we really want to know is what is the derivative of any one of these elements of Z with respect to this guy. If you know what this is, then the entire formula is clear. We can implement it and compute the derivatives. Right. So let's look at what this is. Now I'm going to take an example of one Z channel. Again, there are many channels, right? Many output channels, output affine maps. I'm considering just one of them. So that one of them has been obtained from a single filter. And that filter has as many channels as the number of input channels. I'm considering only one input channel. So this is A input channel. I'm considering the 2,2 element of that channel. I'm considering the corresponding element of the filter. And we're going to see how this guy is used in the computation of all of these elements. All right. Now I'm using two different codes for the filter. One is color, the other is index. We're going to need both. So when I speak of the red element of the filter, it's the 2,2 element of the filter. When I speak of the pink element, it's the 1,2 element of the filter. So keep this in mind, right? So now to compute the 0,0 element of Z, I'm placing the filter starting at 0,0, which means the 2,2 element of the filter multiplies the 2,2 element of the map to give you the 0,0 element of Z. Okay, is there a pattern? It may not be immediately obvious, so let me take one step forward. So to compute the 1,0 element of Z, I've slid the entire filter to start from 1,0, right? Which means now the pink element, the 1,2 element of the filter, is sitting on top of the 2,2 element of Y to compute the 1,0 element of Z. Right, so Z10 is Y22 times W12, okay? Is this animation making sense? Right. If I take another step forward to compute Z20, now this filter has been placed starting at Z20. That means the green element, the 0,2 element, has multiplied Y22 to give you Z20, right? So Z20 is obtained by, in part by multiplying Y22 by W02. And the same thing happens. As I keep scanning, the same kind of formula keeps occurring, right? Can anybody see a pattern over here? Yes?
So we can subtract the element, the 2,2 minus whatever you have at the filters. 2,2 minus 1,2 will give you.
So basically what we find, we're always looking at Y22, right? We fix this. And so it just turns out, take a look, that the coordinates, take a look at the Z coordinates and the W coordinates. They are the ones that change, right? The coordinates of Z and the coordinates of W sum to give you the coordinates of the Y element every single time. Can you see that in the picture, right? And so this is the formula that you get. Zx for Y22, any element x prime y prime of Z is going to be multiplying the 2 minus x prime, 2 minus y prime element of the filter is going to be obtained by multiplying the 2 minus x prime, 2 minus y prime element of the filter by Y22. This clear to everybody, right? I can also generalize this and say that for any element xy in the Y map, this multiplies the filter element at x minus x prime, y minus y prime, to give you z at x prime, y prime. Is this making sense to everybody, right? The pictures must be very clear. So there's, okay. And so what does this mean? I have zx prime y prime plus equals yxy, wx prime, x minus x prime, y minus y prime, right? So the derivative of this zx prime y prime with respect to yxy is simply going to be the filter parameter weight at x minus x prime, y minus y prime. This clear to everybody, right? It's very simple, yes.
I'm not able to figure out how it would work if x, y were 0, 0. Like if you were thinking about the first element, then the filter would only go over it once, right?
So meaning?
Meaning if the element, like x, y right now is the middle element, that's why the filter went over it 9 times.
It doesn't matter, right? This formula still holds. Not every filter element is going to be used for it. But then, so y00 is going to multiply w00 to give you z00. Y00 is not going to be used for any other element. That's it.
Okay.
That's all, right? Straightforward. So, which means now I can replace this derivative at zx prime y prime by, with respect to yxy, by simply the filter at x minus x prime, y minus y prime. And now we have ourselves a formula. We can just use this formula to compute the derivatives for all the elements of y. Okay. This clear to everybody? Okay, these are simple questions. Who's Tailo? T-I-L-L-O-W. Who's Tailo?
Oh, that's me.
Okay, Taylor, what's the answer to the first question?
Is it true?
Okay, let's see. Let's go to the second question. Who's Arbok? A-R-B-O-K. Okay, second question. Also true. Okay, perfect. In order to compute the derivative at a single affine element, y(lm(xy), we must consider the contribution of every position of every affine map at the next layer, because this guy can in principle influence every single element of every map, right? And so the derivative will require summing over all of those guys. And so here's our formula again, right? The derivative of the divergence for the, with respect to the mth, xyth element of the mth input channel is going to be summing over all of the output channels and all of the locations on all of the output channels. The product of the derivative of the divergence with respect to the z element at this position times the x minus x prime, y minus y prime element of the appropriate channel of the corresponding filter, okay? But this is actually a convolution. Can anybody see why this is a convolution? Yeah.
So a convolution is for like endpoints, we sum the multiplications of I and j elements such that I plus j is m. So that's it.
Okay, that's perfect. But let's see this visually, right? And this is why I want the colors. Now consider this. If I'm computing the derivative of the divergence with respect to y22, right? Now y22 multiplied the red element of the filter to give you z00, correct? Yes or no?
Yes.
Okay, so now when I compute the derivative for y22, I must multiply the derivative for z00 with the weight w22. This making sense over here? Okay. Now, be very clear of this, right? Now, y22 multiplied w12 to give you z10, right? So when I'm computing the derivative of y22, I must multiply the derivative at z10 by w12 as shown by the pink color. Making sense to everybody? What about the next guy? The derivative at z20 must multiply the 20 element of the, or 02 element of the filter, right? The derivative at z01 must multiply the 21 element of the filter. The derivative at z11 must multiply the 11 element of the filter, and so on. And so, if I go all the way to the end, I'm showing you which filter element the derivative at each z element must multiply in order to contribute to the derivative for y22. This clear, right? So what do you see? What is the pattern over here? What happened? Yes?
Feels like you're ranging all the gradient maps of the next layer, like that, in depth, and then you're convolving over that.
Yes, but what happened to the filter? The filter was, okay, you were saying? Can you speak up, please? Is it rotated?
Transposed?
The filter is transposed. It's flipped left to right, top to bottom. Right. So you basically flip the filter and place the bottom right corner of the filter. You place the top right corner of the filter at the location for which you wanted to compute the 2 location, for which you wanted to compute the corresponding y derivative. And then you computed an inner product. So this making sense to all of you guys? And so here's what we do, right? So the derivative for y22 is going to be summing over all of the z's, and it's what it's summing is it's computing the inner product of the z map when the reflected filter is placed with a 0 corner at the location for which you're trying to compute the derivative. Okay, and so that's the formula, right? In general, the derivative at any xy is simply obtained by flipping this filter left to right, top to bottom, and placing the 0 element at xy on the derivative z map, and then computing an inner product. Is the picture making sense to everybody? Okay. And so here's what we are, right? So if I want to compute, so this is the derivative map for z, right? I'm trying to compute the derivative map for y. So here's what I will do. First, I'm going to pad this with, if the filter is k, size k cross k, I'm going to pad this with k minus 1 zeros on either side and on top and bottom. I'm going to flip my filter left to right, top to bottom, so that the 0 element ends up over here. Then place it like so, and simply perform a convolution. This making sense to everybody? And that's going to give me the derivative for the y. Very pretty, right? There's nothing particularly fancy. You don't even have to think very hard about the math. But then again, every y influenced every z. A y element didn't influence just one z. And so how do we deal with that? Here's what you're going to do. So there are, in this case, a certain, a bunch of output maps, right? Corresponding to every output map, there was a filter. Now, if you consider the mth input channel, the mth input channel interacted with the corresponding channels of all of the filters in generating the output maps. So we're going to pull out all of these guys. So these are what I've plotted over here. These are the mth channels of all of the filters. And then these are the derivative maps for all of the z's obtained by backpropagating. These things are going to be padded with zeros on every side. These filter channels are going to be flipped left to right, top to bottom. So basically the entire filter is transposed. And then this flip filter is basically just placed on top of the derivative maps, and you perform a convolution to obtain the output. Does this make sense to everyone? Right? So I actually have a little animation which just shows you exactly what happened. Now, the math is clear. The math leads to the operations. You also see why the filter itself must be flipped and why the whole thing is just a convolution, right? Any questions? Any questions? Okay, there's one issue with size. Why do we need to zero pad? Is there an eraser over here? I'm sure. Why do we need to zero pad? So here's a general rule for computing derivatives. This is something that I want you to remember. That, or gradients to be more precise, right? So if I have any process at all, anything, I'm just calling this a process. It can be a function, it can be a convolution, it can be a pooling. It does not matter, anything. And if the input is some m cross n, and the output of this is eventually used to compute the derivative, computer divergence, then every one of these m cross n elements is effectively influencing this guy, right? So when you compute a derivative going back, what must the size of the divergence be, or the gradient be? Same as the input. The derivative at the input should have the same size as the input. It must also, the gradient must also be m cross n. Right, this is a principle that we're going to follow. If this doesn't hold, then something is broken, okay? Now, we are performing a convolution, right? So when we perform a convolution, what were the rules of the sizes of the convolution? Over here, let's say I had an m cross m input. I had a k cross k filter. What was the size of the output? Do you remember? Mm-hmm. M minus k plus 1, right? So this was going to be m minus k plus 1, m minus k plus 1, right? Now when we come back computing derivatives, the size of the map of derivatives with respect to the divergence is going to be the same as the size of z, right? If I directly convolve z with this one with this guy, what would the size of the output be? M minus k plus 1? Minus k. So I've lost another k plus 1, right? So the derivative going back is going to be just this much because I've lost 2k plus 1 going back, right? How do I compensate for it? I pad k plus 1, k minus 1 on either side. And so now when I add this whole size becomes m plus k minus 1, right? And then if I lose a k minus 1, I come back with a size m. So the padding makes sure that when you go back, the derivative is the right size, right? This is clear to everybody, why the zero padding is necessary. It also helps you place this filter at the top left corner. There's a bunch of zeros, and this should answer Ankit's question from way back when, right? But that's, it makes sure that the output size is right. Questions? Okay. Now, if we zero padded the Y maps going forward, which we said we would do if we wanted to maintain the size, then as you're going backward, you're really getting the derivatives for the zero padded input. And then you're going to have to throw away the zero pad regions. Here's a poll. Okay. So who is Weedle? W-E-E-D-L-E. So Weedle is absent. Who's Kabutops? K-B-U-T-O-P-S. Is that right?
Yeah, Kabutops.
Who's Kabutops? Also absent. Nice. Who's Spinarak, S-P-I-N-A-R-A-K. Who's Spinarak? Nope. There's no Spinarak in class. Okay. There's a Smoochum. Who's Smoochum? S-M-O-O-C-H-U-M. Who's Smoochum, guys? That's 5 in a row that I'm missing. Okay. Who's Genjar? G-E-N-G-A-R.
Gengar?
Gengar. Who's Gengar? 6. Okay, when I hit 10, all of you are absent. Okay. Who's Horsey? H-O-R-S-E-A. 7. I'm counting. Okay. Psyduck. P-S-Y-D-U-C-K. Who's Psyduck? 8. Okay.
You check the chat real quick, sir.
Who's Carvana? Can you check the chat? Are they replying? Please track the Zoom chat, right? Who's Carvana? C-A-R-V-A-N-H-A. Okay, and who's Pidgeot? P-I-D-G-E-O-T. Okay, we have hit 10, guys. I'm going to mark all of you absent. I'm sorry. This is, it's collective punishment, but this is the way it is. The next time one of your friends decides not to turn up in class, let them know that they are responsible for your losing a mark. Just take note that everybody's marked absent for today. Can somebody answer that first? Tell me the first statement is true or false. True. Second one. True. Third. Fourth. False. Okay, I won't bother with these things for the rest of the class because all of you are absent. Okay. So to compute the derivative with respect to the mth activation map of the Lth convolution layer, we must select the mth planes, the mth maps of all of the L plus 1 filter layer filters. The selected filters must be flipped and they must convolve the derivative maps after padding, right? That's about it. Okay. And so this, we know, can now be computed using a convolved and flipped filter. I have some pseudocode for it, I'll skip it, right? So we know how to compute the derivative for y's. What about the derivative for the filters themselves? What do they look like? So now, let's consider any specific filter element. Let's say I want to consider, there's this 9-element filter. Let's consider the central element, the blue element, right? Dark blue. Is it used in the computation of every one of the outputs? Yes or no? Yes. Right? But so that is one channel of one filter, and it's used in the computation of every one of the outputs of only the channel corresponding to that filter. It doesn't affect the remaining output channels, right? So if I want to compute the derivative for, say, the blue element, I have to sum over all of these guys. And so here again, let's see how the filter element influences the output. I'm looking at, so the pink element of the filter. All the yellow boxes are the input channels, and the gray box to the right is the output channel. And then you can see that the pink element over here, which is the 1, 2 element of the filter, multiplies the 1, 2 element of y to compute z00, right? It multiplies the 2, 2 element of y to compute the z10. It multiplies the 3, 2 element of y to compute the z20, right? You can see how this is used in the computation of every element. Do you see a pattern? We've seen this pattern before. Do you see a pattern? What is it? Again, remember, we said that the sum of the W index and the Z index was the Y index, right? So just flipping that around, you're going to see that the sum of the Y index is simply the sum of these two guys. Yes?
Since Jeffrey is absent, just pretend I am a pigeon who is like got snuck into a class. So just out of curiosity, let's say that we have a slice of a certain filter, right? So what you're saying is that all these weights, no, what you're saying is that a certain weight in that slice of that filter, it perturbs like all of the elements in the output channel corresponding to that filter, right?
Absolutely.
All right, pigeon out.
Thank you.
I was going to say plover, but I forgot. I'm actually plover.
Okay, does the pigeon have a D in it? There's a pigeon amongst the Pokemons, right? Anyways, all right, so we literally have this, right? So the W12 multiplies y x plus 1, y plus 2 to get you z x y. So now, what is so in general, wij would multiply y at x plus I, y plus j to give you zxy, right? And so if I want the derivative of zxy with respect to wij, that's simply going to be y of x plus I, y plus j. Is that obvious from everybody to everybody, right? Straightforward, right? And so if I want to here's what I have. The derivative of the z value at any xy with respect to the filter element at ij for any channel of the filter that actually produces that z is simply going to be the y at the same channel as the filter channel at x plus I, y plus j, right? And so now if I want to compute the derivative of the divergence with respect to any w, I'm going to have to sum over all of the xy elements of the output channel that it generates, right? And then over all of those elements, I'm going to be summing the product of the derivative of the divergence with respect to z times the derivative of the z element with respect to wij, right? This is just a straightforward chain rule. And this guy, that has already been computed. And this we just found was y at x plus I, y plus j. So I can just plug that in here. And so I have a formula for computing the weights. Everybody clear with this? And can everybody see that this is also a convolution? Is this a convolution? What kind of a convolution is this? Yeah.
It's like you took the Z maps, arranged them in depth, and then you took the Ys and then you.
Perfect, right? So basically, I like the figure, the sound effects. It's beautiful. And so here's what we did. So let's see this guy, right? If I want to compute if I look at, say, W12, W12 multiplied all of these y's to give you all of these z's, right? And so if I want to compute the derivative of the divergence with respect to W12, I'm going to have to multiply the derivative at this z with this y, the derivative at this z with this y, and so on, and then sum them up, which is the same as saying I'm putting the z on this location of y and computing an inner product, right? So also, if I want to compute the derivative with W00, W00 multiplied this y to give you this z. It multiplied this y to give you this z. So if I want to compute the derivative for W00, I'm going to have to place this z derivative map starting at this location and then compute an inner product. This clear to everybody, right? So just generalizing, right? It just ends up being a convolution of the derivative of the z map with the y map itself. So that's the formula up there. If you just work through it, here's what it looks like, right? So in the forward computation, we convolved all of the input channels with the filters to get the output affine maps. Now, if you look at this, say the second input channel is going to be interacting with the second channel of the first filter to generate the first output channel, right? So going back, I'm going to be using the derivative maps out here, and I'm going to be convolving it directly with this guy to compute the derivatives for this W. Make sense to everybody? And so here's what I'm going to be doing. So this is the formula again, right? This would be just if I want to compute the derivatives for the filter that has used the second channel of the filter that generates the first output channel, then I'm going to be convolving the second channel of the input with the derivative map for the first output channel. And this simple convolution is going to give me the derivative of the filter. Is this clear to everybody, operation-wise? And then again, you can check that the sizes work out, right? Yeah, Jeffrey?
The Clover would like to ask another question. So basically, like, you're summing over like all of the like the coefficients of the W are the Y's, right? So summing over all of the Y's that are coefficients of a specific W,
Yeah.
you get the derivative that would respect that specific W.
That's right.
All right, Clover out.
Okay, thank you. So any questions, guys? Yeah.
You still have to do the same padding in this.
Is padding necessary? Now let's take a look, right? So let's check the sizes. What is going forward? What is this size? M minus k plus 1, right? What is this size? M. What is the result of convolving this guy with this one? I'm going to subtract a 1 over here. So that's going to leave me with m minus k. Then I subtract it from that guy. It's just going to leave me with k. So you need to know padding is required. Okay? Questions? Yeah. And so, again, every one of those out, so in order to compute the derivative for the entire filter, that computes the nth output channel. The derivative map for the nth output affine channel is convolved with all of the input channels to give you the derivatives for all the channels of the nth filter. And you can use this in gradient descent, right? So, and if y was 0 padded in the forward pass, it must be 0 padded in the backward pass to make sure all the sizes work out. Questions? Yeah.
What if we adding to our input map when we were doing all?
That's exactly what you're saying, right? If this guy, the input was 0 padded in the forward pass, it must be 0 padded in the backward pass to make sure the sizes match. Okay. Here's your poll.
Yep.
And one call out Pokemons. You're just going to answer this. Somebody is talking really loudly. I think it's amazing. Can you mute them? Yeah, we just got. All right, guys. First statement, true or false? True or false? And the second? Okay, so the derivative for the mth channel of the nth filter is computed by convolving the mth, input channel with the nth output derivative map, right? So we're good. And now, a pseudocode, okay. But then here's the beautiful thing. We've seen a lot of math. We've seen how this becomes a convolution. But sometimes code is even simpler to deal with. So you can do the whole thing, the computation of derivatives, without understanding a single line of the math or trying to understand how anything was computed, just by looking at the code and just doing the right things in the code. We're going to use a couple of simple rules. If y equals sigma of x, then dl over sigma of z, then dl over dz is dl over dy times sigma prime of z, right? Straightforward. If z equals wy, then dl over dy is dl over dz times w. You're adding it. And dl over dw is dl over dz times plus equals dl over dz times y. There's a plus equals, right? Because many terms will contribute. So these two simple rules are sufficient to compute all the derivatives you'll ever need. How's that? Here's my convolution written out in the forward pass explicitly. Every element of, every single operation written out. And so what I would be doing is, I'd be going through the layers. Then I'll be scanning left to right, top to bottom. At each position, I'm scanning over the face of the filter, computing an inner product between the weight and the y, and then summing them all up, right? And then finally, I apply an activation. And so let's forget this last layer. We call it back propagation. So back propagation literally is just doing the entire operation backwards. So here's what I can do. I can flip this And now I'm going to be doing the same thing, except the order of all of the loops is reversed. It's within each loop I'm going in reverse order. That's it, right? Because it's back propagation. Now, the last step we performed here was to apply the activation. So the first thing we are going to do is to compute the derivative of the activation using a very simple rule. Again, this is element-wise, right? Very straightforward. And then over here, the operation we did was z plus equals wy. So going back, I'm just going to say the derivative of y plus equals dz times w. The derivative for the w plus equals dz times y. All I did was flip my code, and the whole thing just works. And there was no complicated math to understand. So if you're performing some operation for going forward, you can just flip the whole thing. And just use, because all of these functions are either activation functions or sums of products, it's easy to reverse engineer the whole thing. Right, anyways. So we've finished with the convolution layers. We figured out how to compute the derivatives for affine maps from activation maps. And given the derivative for the activation maps, we figured out how to compute the derivatives for the previous layer, as well as the derivatives for the filter. So everything has been taken care of. The other thing we are looking at is pooling layers. How do you compute the derivative of the input to a pooling layer given the output of the pooling layer? Now I'm going to assume that we are starting by 1 as before, right? So now we saw two kinds of pooling. What were those? Max and mean, right? So max pooling, you looked at groups of elements, and within each element, you just pick the largest value. Now tell me this, yes?
Could you go back to the derivative loss with respect to the input? Because I'm really sorry, but I just had like a flash realization, sir. I will try and keep it brief.
Which one
As
here?
a plover, I would like to say that I just realized that the the input, input channel, I guess it influences. First, it influences the loss via each of the output channels, but I just realized that it influences like a specific subset of the elements in each output channel. And the key, sir, is that let's say we have the element in the bottom right of the let's say we have like an element in the middle of like an input channel. So it influences like the top left of the output channel. And the way it influences it is through the bottom right of the filter. So that's why we have that weird indexing.
That's right.
All right, I got it.
Okay.
Over out.
Thank you. So now, going back to pooling. So what we did when pooling was to consider groups of elements and then pick the largest value, right? So here's an example. I have this window, and the inputs are 1, 3, 6, and 5. The output is 6. Now, when I work my way backwards, I'm going to have the derivative with respect to this guy. The derivative is telling me if I perturb the 6 a little bit, how much does the loss change, right? I have to propagate this derivative backwards, right? Will perturbing this 5, so this means I've got to chain how perturbing these guys perturbs this with how perturbing this perturbs the loss, right? Yes, no? Okay. So tell me this, will perturbing 5 perturb the 6?
Yes.
Yes? Yes, no?
5 exceeds 6. 5 becomes the max.
Perturbing it is always by a small amount, right? So will perturbing it by a small amount change the output? Right? Which of the inputs will actually change the output? Only the maximum, yes, right? So so basically at each location, we're just picking the max. Again, remember, we're storing the location of the max and the copying the value. But then, when I'm computing my derivatives backwards for any window, I know that only the maximum element influenced the loss. All the other elements had no influence at all. So going backwards, the derivative of the loss with respect to the non-maximum elements is going to be 0, right? And the derivative with respect to the maximum element is going to be simply the derivative with respect to the corresponding z, because it just got copied over. This making sense to everybody? Right? And so this is easy. And so if I were writing a pseudocode, now when I'm going forward, I'm storing the location of the maximum and then copying the value over. When I'm going backward, all I'm doing is copying the derivative over into the location of the maximum. In my pseudocode, I have a plus equals. Why do I have a plus equals as opposed to an equals? So if I'm striding by one, that element could be the max in multiple adjacent windows, right? And so all of those have to contribute. Okay, yes, Alistair?
What if within 2 by 2 window, 2 of the cells are 6, so they tie at the max?
Then this would go to both of them, because each of them could be perturbed and it's going to change the output, right?
In the initial computation, you only store one max index.
You don't know which of those two you took. Okay, you mean you're storing only one max index, right? So yes. So here's the thing. This is like what I said about the ReLU. If something is right at the boundary, any derivative between 0 and 1 works. So in principle, you'd want to store the indices of all the max values. If you store just any one of them, that's still okay. In practice, it's very unlikely that you're going to find two elements which have exactly the same max value. Good question, right? So what about mean pooling? In mean pooling, I computed the average of all of the elements, right? So I have this. There's my eraser. I have z equal, so ij equals 1 over n. This is the layer, yl minus I. We're just summing over all of the elements within the window, right? Now, if I have the derivative for this guy, let me call this z, just to make sure that we have no notation, no confusion. So how does this, so what will the corresponding derivative with respect to, say, any L minus 1 ij be? What happens? Come on, guys, this is not. So I have this formula over here. Z is just an average of all of the y's. I have the derivative for z. What is the derivative for any of the y's?
1 divided by.
It's just 1 over n. You're basically just copying, you're distributing this uniformly over all of the inputs, right? This makes sense, right? And so that's your pseudocode. Going forward, y is the mean. Going backward, you're just going to be distributing the derivative equally over all the elements of the window. Now, this is in fact just a convolution. It's like taking a 1 over n window and convolving the output derivative map. And so we have seen how the derivative of the divergence with respect to every intermediate output and every free parameter, the filter weights, can be computed. This can be embedded in a gradient descent framework to learn the network. I finished very early today. We had 12 minutes left. So I did skip one element, which is resampling, upsampling and downsampling. We'll deal with that in the next class. This class kind of ends early, right? I think I'm done. Story so far. So the CNN is a supervised version of a computational model of mammalian vision. It includes convolutional layers that comprising learned filters that scan the outputs of the previous layer, followed by an activation, and pooling layers that operate over groups of outputs from the conv layer for jitter and variance. We have optional resizing operations, typically performed through strides greater than 1 or interpolation of zeros. The parameters can be learned through regular backpropagation. Computing derivatives for convolution layers is also just a convolution. You convolve transposed filters with the derivative maps of the output to get the derivatives for the input channels, and you convolve the input maps of the derivative maps of the output for the derivatives of filters. Backprop of pooling operations redistributes the derivatives at the output over all the inputs that actively contributed to it. Any questions? Yes.
In the first class, we mentioned that there is a shared parameter that we have. So how will that translate into?
So this is the entire network is a shared parameter network. And so the reason we actually have, what is a convolution? You're computing the same, you're computing derivatives and pooling them, right? And so basically, that's the whole point of the convolution. So this handles the shared parameter. Think of think of what happens. So the way we said this, if I had the map at any element, then all of these guys, so wait, no. Every one of these would, let me say this. All of these elements would be used to compute one element at the output, right? And so then all of these elements would be used to compute the value over here. And so to compute the derivatives at each of these guys, so this guy is actually going to be used in computing a whole bunch of output elements. Right? Yeah. And so the point is that since the parameters here and the parameters here and the parameters here are identical, you get the convolution operation is going to be pooling over the whole lot. Post this on Piazza, I'll draw a picture for you. Right? But this actually, the math works out. It just handles the business that it's all just a shared parameter network. Anything else? Okay, all right. Thank you, guys. Applause for ending early, I'm sure, right?